Now we'll continue, now that we've created the generalized idea of a field of quotients over a ring. We'll apply it to an example of the integers, our ring, and we'll develop the set of rational numbers. That is, since Z is an ordered ring, we have it to be an integral domain, so it has a well-defined field of quotients, which we'll denote by Q, and this is called the field of rational numbers. Additionally, I'll note in the previous video I said that you can create a field of quotients over any ring. This is not true. In fact, you can only form it over integral domains, and we'll note that integral domains are a subset of ordered rings. Therefore, some ordered rings can be, you can construct a field of quotients over, but not all rings in general, and not even all ordered rings. Within this set Q of rational numbers, we can represent it as the equivalence class of a pair of elements a comma b in z cross zx, and we'll note that a comma b is the same as a comma 1 times 1 comma b, continuing our idea of using fractions in this case to represent elements in this equivalence class. Then if we have that phi of a is the equivalence class of a comma 1 and phi b inverse is the equivalence class of 1 comma b, remembering that we have a homomorphism here, so inverses are respected, it follows that phi a times phi b inverse is the equivalence class of ab. So any rational can be represented as by the product a times b inverse for some integers a, b. We can also note that since we have scale invariance, we can represent it as the product of a times c times b times c inverse for any non-zero integer c. It is often customary to simplify this notation by noting a times b inverse to be a over b, so rationals can be represented by the quotients a over b for integers a, b. This field of rational numbers is an ordered field where we apply what we have before, in that we have a set of p of positive elements defined as a set of rationals a, b, where a is greater than 0 and b is greater than 0. We'll note that you do not need to care about the case where a is less than 0 and b is less than 0, because that's simply a scaling of the case where a is greater than 0 and b is greater than 0 by -1 on top and bottom. To verify that any rational other than 0 can be represented by quotient integers, we'll note that if the integers are of the same sign, then multiplying both by -1, we will get a positive element, so a over b is in P, but if there are opposite signs, then the quotient can never be represented by a quotient of two positive integers, so a over b is not in P. It is clear that if you have two positive elements in the rationals, namely a over b and c over d in P, then we have that a over b and a over b plus c over d are inside P, and the product a over b times c over d is in P. So P can properly serve as a set of positive elements, which we wanted to be closed under multiplication and addition, defined on our ring, field, whatever. We then note that since the natural numbers are countably infinite set, that since the integers can be decomposed as the union of z is the disjoint union of 0, n, and negative n, where it doesn't even need to be disjoint since n and minus n do not contain each other nor 0, then we conclude that the ring Z is also a countably infinite set. We can check that all pairs of integers are countably infinite by Cantor's diagonalization theorem, and since rationals can be embedded in the set of pairs Z cross Z by selecting a representative for each class in Q, it follows that the field of Q is also a countably infinite set. It is also worthwhile to prove this in a more direct way by creating a countable set of finite sets, each of which is the set of fractions with the denominator being a integer. For instance, the set of all fractions with 1 in the denominator, set of all fractions with 2 in the denominator, so on and so forth. And we'll see that each of those sets is countable, so a countable union of countable sets is countable by Cantor's diagonalization. We see that we have another example of sets where we have more subsets, but they have the same cardinality, namely that n is a strict subset of z is a strict subset of q, but the cardinality of n, z, and q is all aleph null. With that, we have a fantastic place to stop before we continue by considering fields in more depth, namely the idea of a complete field. And we are going to use that to extend our set Q into the real numbers, which are a natural extension of the rationals, and will be very useful in the future. Thank you.